All right, stats. So we are going to try to go through 9.4. And once again, filming from my car to try to keep the noise level down. If you hear some noise in the background, it's probably the wonderful Canadian geese that like to just never stop making noise around my home. So here we go, 9.4. So before I look at the questions, I really just wanted to try to emphasize the importance here of the 4 steps when we are conducting either a confidence interval or a significance test for the difference between two means. Now, basically, when you guys are looking at this, I'm only going to pull up the test, but for the confidence interval, you're just not doing steps 2 and 3 and 4. You're really just saying I'm going to talk about a confidence interval, check the conditions, and then interpret my interval. So let's take a look. The first bullet point for a significance test for the difference between two means is the samples have to be random and independent if we're talking about a survey. And in the case of an experiment, we want the 2 treatments to be randomly assigned to the units. We need to notice that it says 2 samples look as if they come from normally distributed populations, notice the plural, or the sample sizes, again plural, are large enough that the sampling distribution is approximately normal. The 1540 guideline will be used to determine how much of the normality we need to check. And then the final condition is only used for the surveys, but in the case of a survey, population size should be at least 10 times as large as the sample size for both. Remember, in an experiment, we just skip over that. So then you're going to state your hypotheses, again plural, and you can write them, notice the or in there, either using the notation to the left or the notation to the right. Now, the thing about the null hypothesis is it can only really be written one of the 2 ways in the paragraph. So either you can write mu sub 1 equals mu sub 2, or you can write that the difference, mu 1 minus mu 2, equals 0. I'm always a big fan of the first one, the mu 1 equals mu 2, but it really doesn't matter. It is very important, though, that you specify which one is your mu 1 and which one is your mu 2. When it comes to the alternative, make sure that it matches accordingly. If you use the one I like, you should be using the left column. If you use the other version, the mu 1 minus mu 2 equals 0, then you should be using the right side column for your alternative hypothesis. If you always assign the larger mean value to mu sub 1, then you should really never be picking an alternative hypothesis of mu 1 less than mu 2. You should really be coming down to, am I just checking if they're different, which is mu 1 not equal to mu 2, or is the first one larger than the second? Now, step 3 says we will compute our test statistic. Remember that this is a t, so the test statistic is t. The p-value, which on the calculator does just say p, and it does say draw a sketch. We will be skipping that per usual. But if you wanted to, you can have the calculator draw the sketch if you wanted to see how extreme it was in a visual context. So then we're going to write our conclusion just like we have written all of our conclusions for significance tests. We will compare our p-value to the level of significance, alpha, and we will be a little more open-ended in this section. So let us go down to the questions. The first question I had you guys do was number 53 in the exercises. So we are going back to Kelly. You might remember we had some questions about Kelly and her hamster experiment. So basically what she did was she took very few hamsters. She only had 4 in each group, and she assigned them to either be in daylight a long period of time or daylight a much shorter period of time, and then measured some sort of enzyme in their body afterwards. The results are displayed in this left column. So the hamsters that were exposed to shorter amounts of light had a higher concentration of enzyme. As you can see, the 4 dots are all to the right of the 4 hamsters that were exposed to longer amounts of daylight. You can see the 4 dots are all to the left of that same axis. So it says, are the conditions met for inference about the difference of the 2 means? So did she randomly assign the hamsters to these treatments? Yes, she did. So that part was good. Now, the sample size / normality. Well, this is where things get kind of interesting. We have very small sample sizes, which means that our distribution should be approximately normal. But how do you honestly tell if something's approximately normal when there's so little to go on? And the truth is, you can't. You can't really tell that it's approximately normal. You'd like it to be consistent, but realistically, normal, I mean, you need much more data to know if something's normal. So we're going to go ahead and just continue as if that step had been achieved. And what we really want to make sure is that the results are very definitive. If we get one of those wishy-washy results where the p-value is maybe between 1% and 10%, I don't think that we could literally say that it was very much definitively significant. Now, they're not going to ask us to run a test. They're actually going to ask us to run a confidence interval, which means when we're looking to see if 0 is in the confidence interval, we're going to see just how far away 0 is from our interval, if it's significant. If 0 is in the interval, then it doesn't matter. We've just sort of shown that there's not enough evidence to prove that the light concentration mattered. But if 0 is not in the interval, let's see how far away it was. So we're going to be constructing a 95% confidence interval. So if I come up here to my calculator, you will see that I have already inserted the data. What I'm going to do now is I'm going to go to Stat, and I'm going to go over to Tests, and this time I will be picking the 2-sample interval, okay, the T interval. Now that's option A on my screen. So if I hit alpha and then press the math button, that'll bring up option A. Oh, I lied. That is the 1 proportion interval, so let me try that again. So sadly, this thing lags a little bit, so yeah, the it was option 0. There we go. All right, now I was given the data, not the statistics, even though it was a very small list of data. List 1, I'm happy with putting in the first set of hamsters, which were the ones exposed to the shorter amount of light, and list 2 will be the ones exposed to the longer amount of light. Frequencies are just 1 and 1, as I did not put in frequency lists, and it did want a 95% confidence interval. Remember that for the pooled thing, it's one of those things, if you somehow know that the standard deviations of 2 populations are about the same, you can pool your data. There's almost no real-world scenario where you're going to pool your data unless you have concrete evidence ahead of time. Pooling is one of those things you can do after you've had experience running a test, and then after the fact you want to go and try to replicate those results. You can do some pooling. We're never going to go that deep, so you'll just always select no. And this is taking quite a while, but there we go. All right. So you can see that I did in fact get a confidence interval where both values are positive. 0 is not in my confidence interval, which means that I have achieved a result that is in a way statistically significant. Now you'll notice that my lower boundary is only 0.5. Now the units that are on these things is this enzyme concentration, which is in milligrams per 100 milliliters. Now, do I know if 1/2 of a milligram per milliliter is a large amount in the context? I really honestly don't, because I don't have a lot of familiarity with this information. But if somebody were to tell you that 0.5 milligrams per 100 milliliters is a very significant increase, then I guess whenever we are asked the question in Part C, you are 95% confident that something is in the interval you constructed. What is that something? So I am 95% confident that the difference between the mean concentration of the hamsters that were exposed to a short amount of light and the hamsters that were exposed to a longer amount of light will achieve a enzyme concentration of somewhere between 0.5 and about 9.5 milligrams per 100 milliliters. So I feel like you would need to be a more experienced person in the field to know if 0.5 milligrams was a very significant increase. When I see a gap of 0.5 to 9.5, kind of makes you feel like 0.5 is probably not a huge number. So I feel like, in my opinion, maybe these results, even though statistically significant, might not necessarily be all that accurate because, of course, we had very small sample sizes and it was really hard for us to tell if these distributions were normal. With a larger sample size, we could have been a lot more confident in ourselves, not just the value. So part D says, does Kelly have statistically significant evidence to back her claim that the observed difference in enzyme concentrations between the two groups of hamsters is due to the difference in the amount of hours of daylight? And I think we can say that statistically speaking, yes, she does have that evidence. However, I would probably want to put a little asterisk beside my answer stating that because we don't know if the original data sets are normally distributed, our results rely on knowing whether that information would in fact be true. So if we could say definitively that they are in fact normally distributed, then I'm pretty confident in saying yes. If I'm not sure, then we're not sure. All right. For question number 55, it says the inflammation caused by osteoarthritis of the knee can be very painful and can inhibit movement. What's interesting here is we actually don't end up doing the thing they talk about. They're going to attach leeches to people to see if it helps relieve some of this pain, but the data we're going to be analyzing is all pre-data. Data after they've divided up the groups, and then they've just simply asked them. So the first thing they want us to look at is it says the statistics below are based on their pain levels. I find it extremely amusing that the average pain level here is in the 50s, because that probably means that they ask these people for their pain on a 1 to 100 scale. And that seems like a very broad scale to ask a human being to give their pain level on. But regardless, we're going to judge their pain based on this scale that at least goes up into the 50s. All right, and it would like us to construct and interpret a 95% confidence interval for the difference in these means. So you'll notice the sample sizes are not equal, and that's okay. You do not have to have equal sample sizes in order to compare these. So we're going to check the leech data, and we're going to check the topical gel data, and their question to us is, are these results basically not statistically significant? They want them to be not statistically significant because they're hoping that the two groups basically have the same amount of pain going into this experiment. They want them to be very equal groups. So let's check that data. We will still be running a 2-sample interval. So I'll press stat. I'll go over to tests. I'll pick option 0. But this time I am not given the data, I'm given the statistics. So this is giving me the data from the last thing with the hamsters, but we're going to put in our new data. So for the leech group, it's 53, 13.7, 24. So 53, 13.7, 24. Then I'm going to go ahead and put in the topical gel group. Their average, 51.5, 16.8, 27. So 51.5, 16.8, and 27. Again, it wants a 95% confidence interval, as you can see. And then we will leave the pooling as a no, and we will come down and calculate. Last time it took a little time. Let's see if it goes any quicker. I don't know if you heard the geese last time, but they were starting to really get angry. So, believe it or not, this is a good result for us. We ended up with 1 negative value, 1 positive value, which means that 0 is in the confidence interval. We've basically shown that these two groups are very comparable. You're almost just as likely to have one group be 7 units higher than the other, or as much as 10 units lower than the other, or vice versa. So that's what we want. We want 0 to be in the interval. We want this interval to be as even around it as possible so that we can say, yes, the two groups are equal. So in terms of pain going into the experiment, they did a good job of making sure that they randomly assigned. The next factor they'd like us to take into consideration is the body mass of these people. They talk about how this is a factor that definitely would contribute to knee pain going in, and so if you ended up accidentally with a group of much larger individuals compared to a group with much smaller individuals, it might have more to do with their body mass than it does with the actual treatment that they're about to provide to them. So, if I look at those numbers, the truth is, I don't think we even need to run the result. I mean, look at those numbers. They're closer, the standard deviations are identical than the previous group. So I already know going into this that confidence interval is going to have 0 in it. So because of that, we're going to go ahead and just look at the solution to that section. Okay? So if I come down here to part B, apologize. you can see that the calculator answer is near the top. And it says we're going to get negative 1.587 to positive 2.5867. Okay? And you can see once again that 0 is definitely in that confidence interval. Now they did ask me to go ahead and give an interpretation of this, so if I did have to interpret this one or the previous one, let's look at the interpretations. So for part A, interpreting, notice where it says give the interpretation towards the lower half of the left column. A 95% confidence interval for the difference in the initial mean pain levels is negative 7.092 to positive 10.092, which includes 0. And then for this one, top right side column, you're 95% confident that the difference between the mean body mass indices of the two groups is in the interval of negative 1.587 to positive 2.867, again, including the number 0, telling us that they did a good job of randomization. All right, the next question you were assigned was number 57. We're once again looking at the statistics students who were given the task of trying to find the midpoint of a piece of paper, I suppose, and it was either placed vertically or horizontally, and then all they had to do was just try to place the midpoint. Now, you'll notice that the results once again give us two different sample sizes. That is okay, not a big necessity. The question I really have is normality. So when I go to plug these numbers in, you will see right off the bat, these are not huge sample sizes. The left side column has what appears to be just over 15, and the right side column has right around 15. So because of that, that means we want these to look decently normal. They can't have any extreme skewness or extreme outliers, but we can still proceed. Now let's look at A. Before beginning the experiment, the instructor believed that students tend to make larger errors when line segments are on the vertical line than when they are on the horizontal. Make the necessary changes. Now, since it says larger errors in absolute value, we don't really care about whether they were too far to the left, too far to the right, too high or too low. What we care about is how far away from 0 they are. So all we have to do to get this data put in is simply replace the negative values that are in the two columns with positive values. So you're going to notice, I have a second browser open here where I've inserted this data, that I have just put every single number in as a positive value. Now, the next question actually says, conduct a significance test showing all 4 steps. So now it's time for us to really dive in. So, were these random samples of students? Well, the simple truth is no, they weren't exactly random samples of students. But you'll notice in the parentheses it says we aren't told if the assignments were random, but assume they were because the experiment was done in a statistics class. So we'll go ahead and assume that the teacher properly assigned the horizontal papers and the vertical papers to their students at random. Okay, so now we can say that that condition is checked. Now we're going to check for the normality of these two groups. So let's see what we get. If I hit second, y equals, that takes me into my stat plot. I need to make sure it's turned on. I like the box and whisker plot to do my analysis on. I think it's the easiest one to interpret. And the first one we'll check is the list 1, which was the vertical lines. I'll do that by pressing zoom 9. So that box and whisker plot certainly has some right side skewness, but I don't see any extreme skewness, and I don't see any outliers. I think, even though it's not the largest of sample sizes, I'm okay to proceed. Now I'm going to go straight back to the y equals, and I'm going to check the second list of data, which is L2. Once again, hitting zoom 9. That one has a lot more right side skewness, and it was a slightly smaller sample. I'm not exactly thrilled with this result. So honestly, when it comes down to the second condition, I think we're very borderline. It's one of those things where if you're giving your analysis, you would want to certainly talk about how the second condition isn't specifically met, but probably doesn't specifically fail either. This is right side skewness, but is it extreme skewness? That really comes down to what you consider extreme. A lot of these things do not have definitive, answers to them. So yes, it's skewed, and it stinks that there's no left side bar of any kind, but at the same time, there's also no outliers either. So it is one of those things where it certainly could be a lot worse. So we will go ahead and proceed anyway, even though maybe the data is not as accurate as it could be. Hopefully, our result will be so conclusive that it doesn't matter. So what exactly is going to be my null hypothesis? My null hypothesis, I'm going to choose to use mu1 equals mu2. My mu1 will represent the average amount of error a student makes when trying to place a midpoint on a vertical segment. My mu2 will be the average amount of error that a student makes when trying to place the midpoint on a horizontal segment. My alternative hypothesis, based on the teacher's recommendation, is that mu1 should be in fact greater than mu2. So let us go to our test. This is going to be a 2-sample test, which you can see on the screen as option number 4. So I did insert the data into list 1 and list 2, which is where it will reside. My alternative hypothesis, which is down here in this row, is going to be greater than, so mu1 greater than mu2. Again, we will not be pooling our data. If you wanted to see how this looked in a graph, you most certainly could go to draw, but we just want to calculate. So on this screen, your most important things to take into account are t, the test statistic, which is about 2.09. Now we know from a z-score standpoint, that's pretty far to the right. In terms of a t, based on a sample that we had, this is, extreme, but not crazy extreme. This resulted in a p-value of 0.0239, which basically is just under 2.5%. So this kind of puts us in that wishy-washy range. When I go to make my final conclusion, I can say that this result is statistically significant at 2 of the levels, the 10% level and 5% level. It's not statistically significant at the 1% level. Now, do I trust that this percentage is all that accurate based on that second samples distribution? Honestly, I'm not sure. But it is one of those things where if we just make our conclusion based only on the values given, then I'm going to say that I reject the null hypothesis at the 10% and 5% levels. And by rejecting the null hypothesis, I would say that there is evidence to support the teacher's claim that students tend to make larger errors when doing a vertical line segment and trying to find the midpoint than they do when using a horizontal segment and trying to find the midpoint. However, at the 1% level, because the result is not statistically significant, I do not reject the null hypothesis, and therefore I would not have enough evidence to support the instructor's claim, and I wouldn't be able to say that the one segment is more likely to result in error than the other. So that's a pretty complete analysis of that. Could yours have a little bit more in it? Certainly. Does it have to have absolutely everything I said in it? Probably not to the extreme extent that I've gone through, but you want your analysis to be very, very complete as such. Now, question number 59 is it talks about warm and humid parts of the world, it talks about termites, and it gives some data. Now, the hardest part of this question for most students, I find, is that the way the data is presented is a little bit misleading. I've actually had students in the past who accidentally decided to put the dosages in as one group and the surviving number of termites in as another group. Oops, that was not what they were looking for. In fact, that left side column of dosages is just telling me what your two groups are. The group of termites that received a 5 milligram dose and the group of termites that received a 10 milligram dose. It's the same as them classifying the line segments up above as either horizontal or vertical. So those numbers should not be put into your list at all. One of your lists should contain the first few numbers: 11, 11, 12, 12, 5, 9, 6, 10. And that's it. Your second list should contain the 10 milligram numbers only: 16, 13, 1, 0, 0, 0, 0, and 3. So you should only have 8 values in each list. If you didn't insert them into the calculator that way, don't be surprised if your numbers are wildly incorrect when we look at them. Okay? Are the conditions for a 2-sample test met here? I think it's very clear that on the 5 milligram dosage, you're fine. The data is fairly consistent. You can see in the dot plot that most of it's squeezed towards the middle, and even though 8 is a pretty small sample size, I don't think there's anything extreme about that. You look at the 10 milligram dosage, though, and you realize this one is highly, highly skewed right and likely has outliers, which means that no, we should not even be proceeding with this data set because the results will not be reliable. So, not exactly the best start. But then, of course, the book gives us Part B, which says regardless of your answer to Part A, carry out an appropriate test. So the only test we can really conduct on this is, once again, a significance test for the difference of two means. I will be assigning mean 1 to the termites who survived in the 5 milligram dosage, and I will be assigning mean 2 to the termites who survived given a 10 milligram dosage. And we'll want to write our conclusion in the context of this study when we get to that part. You'll notice Part C says, what are your main concerns about your conclusion? And we'll just talk about that before I even run it. My main concern is the fact that the 10 milligram dosage is really not a normal distribution, which means that that condition was not met. My other big concern, of course, is that they have two very small sample sizes. 8 and 8 are just not very large, which means I can't really say that the results are going to be all that reliable. Now, I know some of you might like to see me put this in on the calculator, but I would like to speed this up so this is not the longest video. Let's go ahead and roll here. So, if I look at the results for number 59, it says, no randomization is mentioned in the assignment of the treatments to the units. The experimental units here are the 16 dishes. The distributions are not symmetric, and the dish with 10 milligrams of resin is highly skewed. Experimental groups of size 8 will not be enough to compensate for this skewness. The conditions are not met. For Part B, they've written it all out completely in words. So the mean number of termites remaining if all dishes had received a dose of 5 milligrams of resin is equal to the mean number of termites remaining had all dishes received 10 milligrams of resin. Or basically, mu1 equals mu2, where mu1 is the average that received 5 milligrams and mu2 is the average that received 10 milligrams. They went into extreme detail. I would not expect you to write it as detailed as they just did. The alternative hypothesis is that mu1 does not equal mu2. I find it a little confusing that they decided to assign the 1 and the 2 to the 5 and the 10. Obviously, we know why they would choose those numbers, but I don't want you to be confused. It still just means 5 milligram dosage, 10 milligram dosage. So if you were to plug in those 8 numbers in list 1, the other 8 numbers in list 2, run a 2-sample test, you should have ended up with a test statistic of 2.153, giving you a p-value of 0.0589 or 0.588 according to this. So because of that p-value once again being very wishy-washy, let's come down to our conclusion. It says at the 10% significant level you would reject the null hypothesis. However, you would not do so at the 5% level or, of course, the 1% level. You do not have statistically significant evidence at the 5% level that the size of the dose makes a difference. You do have statistically significant evidence at the 10% level. Going back to Part C, you can see they're just kind of reaffirming what I said earlier. The main concerns are the lack of randomization and the skewness of the distribution of termites is surviving in these rather small experimental groups, especially the 10 milligram group. The experimenter should repeat the experiment, randomly assigning the treatments and using a larger number of dishes. So there you go. All right, the last question that I had you guys look at was actually question number 63. So right side column. Refer to Kelly's hamster experiment. What kind of error could Kelly be making in significance test of the difference in the mean enzymes? Remember, we saw two positive numbers, which as a significance test would be the same as getting a small p-value, causing us to reject the null hypothesis. When you reject the null hypothesis, the only error that could have been made is rejecting something that might have been true, which, if we check the book, hopefully, they're going to tell us is in fact a type 1 error. So Kelly rejected the null hypothesis. If the null hypothesis is actually true, she would have made a type 1 error. The rest of the question here says, what should Kelly do in a similar experiment if she wants to reduce the probability of making an error of this type? Remember that errors of type 1 cannot be affected by sample size. I know that we want to say bigger sample size is better, and it is, but it doesn't change type 1 error. The only way to avoid making type 1 errors is to increase our confidence. And if we increase our confidence, we decrease our level of significance. Stating either one of those would be correct. Remember, the problem with doing that is, especially with a confidence interval, whenever I give somebody my values, the values are going to cause the interval to be much wider. So I lose that precision. I can't be as precise with my answer, but I do avoid making a type 1 error. The book says she could decrease the level of significance to 0.01. A 99% confidence interval will then include 0, showing us why using a 95 and using a 99 there would change her entire result. Okay? Finally, in part C, what about this situation gave Kelly power to reject the null hypothesis even with so much small sample size? And that goes back to what I told you guys earlier, in that if the results are far enough away from 0, then you're still going to have that power. The only reason her results ended up being far enough away from 0, if we go back and look at the data though, and here we go, now it's at the top of the left side column, is the fact that there was no overlap in the data at all. All of the shorter light hamsters are in a higher group. All of the longer light hamsters are in a smaller group, resulting in something that just had to be statistically significant. The problem, of course, is with a few more hamsters, who's to say that that variability might not have increased a little bit more? So there's just not enough data to go off of, obviously. So anyway, guys, there you go. That's 9.4. I know I would have liked to have gone in it in much more detail than I did here. You're going to take your first quiz this week, but think of it as more of a trial run. If they go very poorly, then we'll talk about that. But I think they'll still go pretty well. Remember, you're going to be taking this thing in your home, so realistically, you're going to have every resource available to you. There's really no way for me to stop you from using those resources. So take your time, answer the questions completely. If you have other questions you want to ask me, feel free to email me if you need to. I'll get back to you as soon as I can with those emails. And remember to turn in the quiz that I send you starting on Thursday by no later than midnight on Saturday. So I should send those quizzes out no later, I would say, than maybe noon to about 2-ish on a Thursday. It might even come earlier. But you'll have the rest of Thursday evening to always take those if you want. All day on Friday, all day on Saturday. Just make sure the clock doesn't roll over to Sunday. So guys, good luck with this. Hopefully it was helpful, and I will talk to you again next week.